Okay, so I'm recording this video because it seems like the ComP470 class has not really covered Verilog to its fullest extent. So this is going to be kind of a recap of all of the core aspects of Verilog that you need to succeed in ComP475. Now, this isn't going to be a all-inclusive recording. This is going to be just the stuff that I feel like you need to know to succeed in this class. So I still recommend that all of you review the Compy 470 book so that you can kind of cement that knowledge and kind of have a better, more whole grasp of the information. But I have prepared a few modules that we're going to go through, and I'm going to use them to explain a few things. So first thing, I wanted to just go over like the three major ways that you're going to be writing Verilog code. So the first three major aspects are you're going to be using things like assign statements for just simple um, one line pieces of logic that you need. Then you have module instantiations where you create other modules and then instantiate them in a top module. So you can see that here. And then your third most common form is your always block, which is considered like it's called like a procedural block. Um, I'm not going to go super in depth on textbook definitions for these things. I'm just kind of trying to show you practical applications of all of these aspects of Verilog. So these are the three main forms. You have your always block, module instantiations, and your one-line logic with assigned statements. Okay, so the next part of this that I want to go over is the various variable types that you're going to be working with. So the first, or the main two that you work with when you're writing your module code are the wire and the reg. Um, I'll go a little bit more in detail when I'm showing you the actual actually writing Verilog code, but the main difference between the wire and the reg are that the wire is used when you're assigning to that variable outside of procedural blocks, meaning when you're using things like assign statements, or like I was showed off in the first module, the module instantiations. Anything when a module that you've instantiated is driving that variable. So for example, in this case, dout, um, that variable needs to be a wire. And when you declare input outputs, I'll also talk more about that later when I talk about creating modules. They are defaulted to a wire. But wires, basically the thing you need to know, wires are outside of always or initial blocks. Basically, anytime you have an always block or an initial block, it needs to be a reg. Outside of always and initial blocks, it's a wire. The next concept that I wanted to talk about with wires and regs are vectors and arrays. So basically, vectors are just multi-bit variables. So in this case, variable 1 and variable 2 are both 4-bit vectors, with variable 1 being a 4-bit wire vector and variable 2 being a 4-bit reg vector. Now, when you're declaring vectors, these brackets on the left are what define the size of the vector. Now, be careful when you define these vectors, because they start with 0. Their positions start with 0. So their upper position needs to be 1 less than the size of the variable that you actually need to represent. So for example, in this case, if you wanted to represent a 4-bit variable, something from 0 to 15, you would need that upper number to be a 3. Basically, that 4 minus 1. I'll show that off in one of the other modules using parameters. But for now, just know that your upper limit in this case needs to be 1 less than the actual size that you're trying to represent. Also, one thing to note with the vector declaration here is that if you notice, this side is 0 to 3 going from right to left. Now that is basically just what endian the variable is. In this case, it's the standard form that you're used to working with, which is little endian, where the least significant bit is on the right and the most significant bit is on the left. But yeah, it's just one thing to take into account. You can use big endian, but that's not typical or standard, so you will most likely not use that at any point during this class, but I just thought I'd bring it up. Now, one other major aspect of variables is the arrays. So arrays, for now, for you all, are basically what amount to memories later on. But there are various other uses of arrays in Verilog that you will, if you end up taking Comp 570 as one of your electives, will become much more familiar with, because you can use them with things called generate blocks frequently. But in this class, you'll not be using that, and these will simply amount to what you use as memories. Now you can tell from this that they're slightly different in declaration from the previous two variables vectors that I was showing you. You see these brackets on the right. Now the brackets on the right are basically denoting how many vectors there are in that array. So the brackets on the left are the size of each vector, and the brackets on the right are the vectors in the array. Now, what you'll notice is that they're declared in the brackets differently. So on the left side, I showed you declared the endianness of the vector. Now this, showing the the number in the array, or in the array, basically you'll be declaring this similar to how arrays work in a language like C, where arrays start at 0 and increase in index. So you'll always be making these arrays with 0 to and then whatever the limit that you want is. And similar to the vector sizing, keep in mind that that 0 is included in the amount, so you need to have your upper limit minus 1, basically, be your size minus 1, basically. But that's really it for the main two. Those are all what you'll be using in your actual logic of your modules. The next two are what you use to allow your modules to be more customizable and more reusable. So parameters, those are the biggest, or that's the biggest one. Parameters work similar to constants in a way in C, in the fact that at the time that the program, Vivado, or whatever program you plan on using for running your simulations, will know what that value is at the time that it runs its simulation, meaning that that value will not change after your simulation has begun. Or if you synthesize the module and plan on putting it on a board, those values, once again, only change prior to doing simulation. And once you've ran simulation, synthesis, and all that, those values are made constant so that they can be used to alter various elements of the module itself to allow you to reuse your modules. Local parameters are very similar to parameters with one minor detailed difference. Parameters can be altered from outside of the module. So you can alter parameters in your module when you instantiate it. So you instantiate the module, and I'll show that off in a little bit. You can actually see it in that first slide here. The register that I instantiate has one parameter, the data width, which is the size of the vector of data that the register is, well, registering. And that parameter I set to 32, which means because of that parameter in that register module, it allows me to have a register that I can set the size, and I can reuse that same module several times. You don't need to make a register for every bit width that you'd ever need, because that would be insane. All you have to make is one register with a parameter so that you can change the bit width and reuse it several times throughout your module. So that's kind of why parameters are the key to saving you time when you write your Verilog code. Allows you to reuse things. Now, one key note though is with local parameters, they are not changeable um, outside of the module. So local parameters you can only alter by going into the module itself and changing the number or changing whatever the calculation is. Local parameters are often used with things like finite state machines where you just need an easier, more readable way to use constants. So like if I pull up one of the modules that I'll go over a little bit later, you can see that I use a local parameters to define all of the various states of the finite state machine. Now, that has no effect on the operation of the code besides how readable it is. So rather than having to look at numbers, you can just look at state 0, state 1, state 2, state 3. But with other modules, you can also use them to actually perform certain calculations on the inside that you don't want people being able to tamper with for the security of your Verilog code and the stability of your Verilog code. Now, one other thing before I move on that I want to mention about parameters is, as you can see here, parameters also don't have to be restricted to numbers. You can use parameters with strings as well, which comes into play a little bit later with memories, so that you can basically make it so that you can change memory files on the fly rather than having to constantly go back into your modules and change text there. You can simply, outside wherever you've instantiated the module, update a parameter so that it automatically updates in the actual module itself, so you don't have to keep messing with things, and it just saves you time that way. I'll show you that once we actually get to the memories and how that can be super beneficial, but I just wanted to make sure you guys knew that it is possible for you guys to be able to do that. But moving on from parameters, the last major thing you'll be working with is the integer variable type. Now, in some cases you can synthesize the integer variable type, but you'll never really be working with that in modules. That's not really something that you use in the actual modules that you write that serve functions. They are more useful in the actual testing and test bench portion of working with your Verilog modules, because you can use them for things like loops and stuff, so that when you're running your tests, you don't have to have a test bench that's 1,000 lines of code. You can have a test bench that's a loop that loops 1,000 times and just uses I, like you would in a language like C. So I don't recommend you end up using integers in modules, though in some cases they can be synthesizable. Like I said, I don't recommend you use them that way. Just use them for testing and keep using vectors and specifying the sizes like you normally would in modules. Now, just to show off the other things that I talked about, you can see here how you access the elements in the various arrays that you'll be creating. You access them like you would in any other programming language like C, C++, Java, all of those. You just access them simply with the brackets. Another thing that I wanted to talk about is constants here. You can see there are various different ways that you can define constants. The way that I like to do it often is using defined sizes. So you can just do the number, but when you're working with vectors that you've defined the size already, it's a lot easier and more controllable to define the size of the constants themselves. So if you look here, all of these constants, because I created these variables of size 4-bit, all of the constants that I define here are sized 4-bit. And the notation for this, you can see, is the size, and then an apostrophe, and then the format letter, and then the actual number itself. And the various format letters, the three most common that you're going to use are B, H, and D, with B being binary, H, well, you can see the B here, B being binary, H being hexadecimal, and D being decimal. So basically that's it for the constant aspect. Though you can see here, I didn't do that with this 0. If I wanted, I could have this be 2, and that'll still work, but you've now have a number 2 that you don't know what the size is, though the synthesizer typically chooses 32 initially and then assigns from the least significant bit forward the number of bits it needs. But it's better to just choose the size so that you have more granular control over your code and you know what's going on. And one last thing I wanted to talk about before moving off of the various variable types is part selecting and how you can access certain bits of a variable, which comes into play very often. So for example, I show it here. See, each of these vectors is a 4-bit vector. But let's say I just want to assign a value to the lowest 2 bits. Well, you can do that by part selecting. And what you do with part selecting is you basically can either set a specific bit or a range of bit positions to assign a value to. In this case, I chose the range from position 0 to position 1. If you wanted, you could do the range from position 2 to position 1. And now keep in mind, one of the things that you'll have to think about when you do this is, you see how I'm assigning a 2 to that. Now, normally, positions 2 and 1 are the positions for 4 and 2 for the binary representations. But since those are the only 2 bits present, when you assign this 2, those will treat those 2 bits as if they were the positions for 1 and 2. Meaning that the number, since 2 is just 1, 0 in binary, will be assigned to position 2 and position 1, which are representing 4 and 2 in binary. So you just have to keep that in mind, the range that you select when you do these part selects. But that's it for the basic variable types and how they function. Yeah, so that's the end of this section. Okay, so the next thing that I wanted to talk about in this video is the process of creating a module, and some aspects of module creation that'll help you create modules that you can reuse over and over again to save yourself time and extra work. But before I go into the actual process of creating modules, one thing that I have to say is when you do modules, please do not have several modules in a single file. That's bad practice. It makes debugging more challenging. It makes it harder to have your modules be portable and be able to reuse them. So I recommend you just do one module per file. Now I know having a bunch of files is something that a lot of people aren't used to because they're used to writing C code where you can just put everything you want into one file and import that one file. In Verilog, it's just easier and better for everybody, including yourself, to have one module per file. So it's better off having, if you have a bunch of modules, it's better off having 20 files and 20 modules than one file and 20 modules. It'll just be so much of a pain to try to debug those. So I just wanted to make sure that everybody knew that now, because I knew last semester when I TA'd this class, that was a big issue starting off. A lot of people had files with dozens of modules in them, and it made debugging the code just exponentially more challenging. But now let's actually get into creating modules. Now, as you can see, there's a general format for module creation. Now, the first thing I'm going to be talking about, I'll talk about test benches later. These are functional modules, and they you create them with this format. The keyword module, then the name of your module, and then you have a section enclosed in parentheses that is prefixed by this pound sign here. Now this pound sign and then enclosed parentheses is the section for your parameters of the module. Now those parameters, like I was discussing in the last section of this video, is how you can make your modules customizable. Now, as you can see here, this module that I have is a clock divider module that I created for a different class. And the parameters are the input frequency and the output frequency. And that allows the user of the module to instantiate that module, select the frequency that they have going in, and the frequency that they need coming out. So this basically is now a general purpose clock generator from a higher clock frequency. And you can see how that is super useful in designs where, let's say you only need a couple kilohertz and your clock frequency from your board is in the 100 megahertz range. These can be super useful, and being able to select the frequencies that you need is so nice to work with. And the next section that you see here, enclosed in the next set of parentheses, directly following, is the input-output ports. Now, there is a third mode, in-out, but you won't be using that in this class for any reason, though it does exist. The main two forms that you're going to use are just simply input and output. Now, you can see here that I have input before each and every single one of the ports. Now, you don't need to do that, but I do just for readability and to easily determine. If you wanted, you can just do input and then a comma-separated list of your various port names, and that will work. And then when you start the outputs, just put output and then a comma-separated list of your various outputs. Now, keep in mind, in this case, this module only has single-bit ports, but if I can pull up another module that has more, let's say this mux here, which is another example of the using only one input. You can see here I have input, select, and then the two inputs for the various data inputs, and then the output for the data out. Now you see here I have the ports size defined, which is what you would do if you had a port bigger than 1 bit. Now, as you can see in both cases of the clock divider and this mux here, the comma-separated list does not have an end comma. So you have all your ports with a comma after the name, and then the last port has no comma, and then just the closing parentheses, and then a semicolon. So that's the process of just creating the actual module definition. Now, one other thing I want to talk about before moving on to the next kind of section of this video is local parameters, the power operator, and various functions that Verilog has available. Now, you can see this module is a good use, or a good example of using both parameters and local parameters. So here you have the parameters that I want the user to be able to change, and then local parameters that I don't want the user to tinker with because they are critical to the module's functionality, and if the user alters them in a way, it could very easily make the module not function. And you can see here, you can do math operations with them because they're parameters, and the other values that you're using for the math operations are also parameters, meaning that they're all constant and they can be determined before the synthesis tool like Vivado will actually implement your module, and whether it be simulation or synthesis. So here I have this math operation to determine the half period, and then that also determines how much you need to count to divide the clock. So with that value, I use a function here that you may have not seen before, which is fair. It's not really covered in the book, but this function is called the clog2 function. You can tell by the $sign in front of it that is a function. What the clog2 function does is it is the ceiling of the equation log base 2. And what it does is it takes the log base 2 of whatever value that you feed it, and then we'll take the ceiling of the result. And what you use this for, and why I think this function is very useful when it comes to making reusable modules, is you can use it to determine the bit width of vectors needed to do various tasks. In this case, I'm using a counter, and the counter needs to be able to count down a certain amount of, or count down from a certain number. And to represent that number, you need a certain number of bits. So using the clog function, it can determine the minimum number of bits needed to represent a given value. Of course, the minimum number will have more values represented than it needs. So let's say you wanted a counter that counts down from 10, right? But you want the user to be able to set that number. So they should be able to set 10, 20, 30, 40, 50, 60, a million if they want. But we'll say 10 for now. To represent 10, you need, you do log base 2, which would give you somewhere around 3 point something, 3.2. We'll just say that for now. And then you take the ceiling of that as 4. Now you can represent that number 10 with 4 bits, meaning that you can represent 0 to 15. Now you may not need the 11 through 15, but you absolutely need those 4 bits to represent 10. So that's why this function, and there are some other functions that you can use. You can also create your own functions. But I just wanted to highlight this function in particular because of its unique usefulness. And then one other operator that the book doesn't discuss that I wanted to discuss here, because you can use it when creating memories, which I'll also further discuss it there, is the power operator here, this double star. Now that is basically just saying 2 to the power of the number on the right. So it's whatever the base is, in this case 2, the number on the left, to the power of the number on the right. But that'll be in more detail later when we cover memories. But other than that, that kind of sums up the process of just creating a Verilog module. Okay, so the next thing that I wanted to move on into, and this is probably going to be the bulk of this, is actually writing Verilog and the various things that you're going to use to do that. Now, before I start actually showing you modules and all that, I want to show you first this section of the book right here, which is all the books, or all the various operators that exist in Verilog. Now, I'm not going to go over every single one of them. This is in the 470 book. It is posted on Canvas. It is in the modules section of Canvas, and it is available for everyone to open and read. But there are a few key ones that I wanted to talk about, one of which is not shown here and is covered in your assignment, or in your assignments. The one that I wanted to cover in the, or go over, is arithmetic right shift, and then the replication, concatenation operators, as well as the ternary operator, which is shown down at the bottom. It's also called the conditional operator. Now, you can see the format for first the concatenation and replication ones here. You can see that it is curly brackets and more in double curly brackets. And then for the conditional, you can see it is a question mark and then a colon. So first, I'm going to go over, though, the arithmetic right shift, because it is one of your assignments. I'm just going to go into this module here and in a comment down here show you what, and explain to you what that is. So the arithmetic right shift is the triple right arrow. And I've seen some people and heard some people ask why there's not an arithmetic left shift. And that kind of comes with the definition for the right shift. And what the arithmetic right shift does is when you right shift a variable with arithmetic right shift, the new bits on the left, so keep in mind, right, you have, let's say you have the binary number 1, 0, 1. If you right shift it normally with just a normal right shift, becomes 0, 1, 0. And that 1 on the right gets lost, and the 1 on the left shifts in. And then it is replaced with 0. Now, normal right shift simply adds a 0 to the most significant bit with when right shifting. Arithmetic right shift will shift in the sign bit. So whatever the sign is. So, for example, with this number, the 1001, that same number, if I just move over further, the arithmetic right shift is 110. And what that does is it allows you to do division by powers of 2 while maintaining the sign. So if you wanted to divide a number by 4 and that number is a negative number, let's say you wanted to divide -8. So let's say you wanted to divide -8. You could use arithmetic right shift by 2 positions to give yourself a -2 because it shifts the sign inward. So that is kind of why arithmetic right shift is important and should be covered more in depth. Now, you can tell from this definition why there's no arithmetic left shift. There's no sign in the least significant bit. When you left shift, you're basically multiplying by a number, and the only thing that's coming in is the least significant bit, which has no weight on signage. So there's no need for an arithmetic left shift because there is no sign there. So there's only really the arithmetic right shift. But that's the arithmetic right shift. The next thing, I have a sign extension module, which you will actually end up making one yourself in the processors. But this sign extension module was a good example of using both the concatenation and replication. So here, let's say you want to sign extend a number. Your input number is 16 bits, and your output number is 32 bits. So what you do is you have the concatenation operator. You can see it on the outside. So it's this parenthesis and that parenthesis. That is the concatenation operator with the comma separating. Now you can concatenate more than 2 things. It's just a comma separated list. So you could have 4, 5, 6, whatever. You just need to separate them all by commas. And that allows you to take the vectors and just put them together. Meaning, if you have 2, let's just say you have 2 4-bit vectors and you concatenate them, you'll have you'll have one 8-bit vector, and it simply just takes the 4 bits from the right and the 4 bits from the left and just puts them together, with the left being the most significant bits and the right being the least significant bits. And then the replication operator, you can see right here with the double curly brackets. So you have a curly bracket here, which corresponds to this one, and the curly bracket here, which corresponds to this one. Now, the inner curly brackets is the bit or bits that you want to replicate. So it doesn't have to be 1 bit. You can replicate 3 bits, 4 bits, as many bits as you want. But the inner curly bracket is what is being replicated. And then next to that is the number of times you want to replicate it. Now, it doesn't have to be in parentheses. Usually you can just do a constant number if you'd like. But in this case, since I'm using parameters like we discussed previously to determine how many times it needs to be replicated, I just put that number in parentheses so it can calculate with the parameters how many times it needs to be replicated, and then replicate it that many times, and that's it. So in this case, you're trying to sign extend a 16-bit number to a 32-bit number. So you need 16 replications of the sign bit. So it takes the out size times the minus the in size to get 16, and then replicates whatever this is, which is just the sign bit. It's the most significant bit of the input number, and replicates it 16 times, and then concatenates it, so basically just attaches it to the original number in the most significant bits, therefore sign extending the number. So the reason why I wanted to explain those two operators in particular is they can be very useful at times when it comes to breaking numbers apart or putting things together simply without having to do a bunch of bit manipulation. Another thing that you can do that I'm going to go over here to show off as well, once again in comments down here, is you can use a similar concept of concatenation with the variable that you're assigning. So let's say you want to have something equal to, and let's say you have two control variables. Let's say you have a write enable A and a write enable B and a write enable C for something. Let's say you have three different registers throughout some design that you're working on, and you have three different enable control signals. And let's say you want to you don't want to do three separate. You don't want to go WEA equals 1, WEB equals 1, and then WEC equals 1. You don't want to do that because, that just takes up a bunch of lines of code, and you don't need to do that. You can very easily do WEA, EB, and EC is equal to 3B111 or 101 or whatever. And then how that works is it will take the 3 bits here, or however many bits of number you provide on the right-hand side, and we'll try to just fill up everything on the left-hand side from least significant bit to most significant bit, being that this number is least significant to most significant over here, and we'll use that same methodology from here to assign those bits. Now, keep in mind, though, if, for example, you wanted to do 4, but you only have 3 bits, this bit right here will be undriven. It'll be a Z or an X. It won't assign anything to it because it has nothing to assign to it. It'll only assign to the 3 least significant. So you have to keep that in mind, that when using this, you need to make sure that the number of bits on this side is either equal to or less than the number of bits on this side. But keep in mind as well, if you have a whole number that you're trying to assign to the things on the left, and this is, let's say you have 4 and this is a 5-bit number. Now that most significant bit is lost. Just nothing, that doesn't get assigned to anything. This just becomes 0, 1, 1, 1. And that's it. So just keep that in mind. I just wanted to go over those, and then there's one other operator that you can find useful because it can basically make, rather than having mux modules instantiated, rather than having mux modules instantiated everywhere or having to do a bunch of if-else statements, if you just have one decision that needs to be made, you can use what is called the conditional operator or ternary operator, which is this line right here. So this is basically just a 2-input mux. And what it does is you have your output vector is equal to, and then you have the condition. In this case, it's the select signal to the mux. That condition now then gets checked. This case on the left of the colon is the true case, and the case on the right in the colon is the false case. Now, you can actually kind of daisy chain this conditional operators if you would like, because you could then go in, and I'm just going to do it down here to not affect the module itself. If, let's say, you have your true and that value you want to be D in, and then you want to check something else, you can then add another one and let's say there's a signal that we haven't declared anywhere called select2, and you want to check that signal, and then you can then have another continuation of that, and then have a true case and a false case, and you can keep kind of daisy chaining those if you would like. Though at that point you're probably better off just doing an if-else statement. But in this case, if you really only have one select or one decision that needs to be made, this conditional operator can significantly compress your code rather than having an if-else statement for that, which would end up being several lines of code. You can have it just thrown onto one line. It makes for easier readability as well as kind of just condensing the code and having less overall lines. And that's kind of why I wanted to go over that really quick. Now, I'm going to assume going forward that you know the rest of these operators. And if not, they are all in the book, so I'm not going to spend time covering every single one of them. I just wanted to cover those couple because I find them either that a lot of people are either confused with them, or I personally find them very helpful. Now I'm going to get started really with the actual process and what you use to write Verilog. Now, before we can really start going into the nitty-gritty of Verilog, you need to really understand your combinational versus your sequential logic. So your combinational obviously just being your simple logic and decisions, and then your sequential being your memories, your time delays, and your things like registers, memories, and all that, flip-flops, latches, memories. And then you have your combinational, So those two things have various effects on how you write the Verilog code. And the most noteworthy of them is the blocking versus non-blocking assignments. So blocking assignments are with just the singular equal sign right here. And non-blocking assignments are this kind of less than equal sign or kind of arrow shape. And the main difference is that blocking assignments like these will wait one after the other to occur. So this module isn't the best example of that idea of one after the other, but whenever you're doing combinational logic, usually a gate is fed into another gate, which is fed into another gate, which is fed into another gate, and all of those together, comprise your logic equation, or whatever you're trying to do in your combinational logic. And each gate requires the input of the next gate. So what it does is it will force the next instruction in whatever code block that you're in to wait for the previous instruction to complete before it continues its instruction, so that it can take the result of that into its own. Now, the non-blocking assignment, which is this one, does not do that. All non-blocking assignments within a code block or within any always block occur simultaneously, which allows you to simulate the sequential logic, because then let's say you had something like this, where you have your current state equals next state, or current state equals state 0. Now, in a larger module where you'd had several things going on, if, for example, your current state becomes your next state or whatever, if there's any change made to that variable at the same time, right? So if in that block of code, a line previous to that added 1 to next state. Let's say there was a line above this that in this else block, let's say here that there was a begin and end, which, by the way, just to let you know, is the begin and end is how you enclose a block of code. Rather than a language like C where you just use curly brackets, you use a begin and end. But let's say in this block you had next state equals, or next state equals 0. What would happen is that this next state would, since it's happening simultaneously, current state would get the current value of next state, and then afterwards next state would become 0. So it means that each, basically everything on the right-hand side when you have non-blocking will, at an instant, go to the left-hand side, whereas with blocking, in order, everything happens in order, basically. So in this case, if these were both non-blocking, or these were both blocking, then it doesn't matter whatever next state was. Next state becomes 0, and then the current state gets 0. So basically, rule of thumb is whenever you're working with sequential logic, like a memory or a register or any of the above, basically you're using non-blocking for sequential and blocking for combinational. It just allows you to simulate that ability of storage and how alterations to it does not affect the next operation, basically. So, in short, non-blocking, the less than equals, is sequential. Anything basically happening at a clock edge. And the blocking, which is just a simple equal sign, is anything strictly combinational, which is not relying on any kind of edge. And that's kind of the big difference with those. Those will, doing those incorrectly or mixing the two up is one of the most common errors that I see in people's code. So just remember, anything at a clock edge that requires an edge change and should only happen at that edge needs to be non-blocking so that it allows everything to transfer simultaneously so that one change prior to that does not alter that assignment. And anything combinational, because it depends on the previous stages of that combinational logic, needs to be blocking to allow it to get the value of that previous stage of combinational logic, or else your combinational logic, if you did non-blocking, would output the wrong values. So that one I just wanted to spend a little bit more time discussing and kind of giving you an idea of how that works, because that is probably the biggest mistake that I see in people's code. And one other thing with sequential logic, before we move on to other things, is basically everything that you do besides a memory, like a full memory, like a RAM or a ROM, anything that uses sequential logic, like finite state machines, simple registers, all of those, I say always have a reset. Always include a reset signal. And you're going to hear that from me several times throughout the semester whenever I see your memory modules, like, and not like the memories like ROMs or RAMs, because those, it's not feasible to have a reset on something that has 1,000 memory locations. But for things like registers and finite state machines, every time I see them not have a reset, I'm going to tell you to have a reset. Because how else is the board or simulation tools supposed to know what state your finite state machine is in when it begins if you don't have a way to reset it to a known value? If you don't know what the value is, it's not going to function properly because it cannot determine what state it is in. So as you see here, my finite state machine here, this is just a simple dummy finite state machine that serves no purpose, but it has a reset. And if I show you my register, it has a reset. Every sequential logic, this clock divider, it has a reset because it sets the counters and the clock to 0. Anything that you do that is sequential logic besides bulk memories like ROMs or RAMs, besides bulk memories, any sequential logic that you do should absolutely have a reset. I cannot stress that enough, especially when you're only simulating it. Because if you're only simulating it, there is absolutely no way for the simulation tool to know what state it is in at the start of the simulation. So you're going to see a bunch of X's, and if that value is not assigned to like a register you can almost get away with it because if you just assign a value, then it's a known value. But with finite state machines or any other kind of sequential logic, you cannot get away with it because it will not know where it starts. There is no way for, if there's no reset here in this finite state machine, there's no way for it to determine the next state because it doesn't even know what state it's in. It cannot determine the next state if it doesn't know what state it's in the first place. So keep that in mind. I cannot stress this enough. Any sequential logic that you do that's not a bulk memory like a RAM or a ROM. Like this is a bulk memory. It has several locations, and it would be not feasible to have a reset. As well as with this ROM, it has several locations, and it would not be feasible to have a reset. But anything other than that, registers, finite state machines, please, please, please put a reset. I cannot stress that enough. But next, I'm going to start going into the tools that you have at your disposal for for writing Verilog, one of which is the case statement. This allows for making large decisions where there's several possible outcomes, and making it so that you can write it in an efficient way rather than having, let's say you have 10 possible outcomes to a decision. Rather than having 10 if statements, you can do a case statement, which is covered in the book, but this is the format for a case statement. You put case, and then in parentheses, whatever your whatever variable or whatever select signal or whatever is deciding the output is whatever deciding whatever the output state is. In this case, there's 4 output condition or 4 output possibilities, meaning that there's 4 different cases that go to an output. In this case, the current state is what is deciding the output of your decision, and you then have as many possible conditions as you want to put in. And this is another thing that I'll talk about in a second. In this case, I only have the next state and current state are both 2 bits, so they can only represent 4 possible cases. So in this case, this represents every possible case. But there is another thing that is included in case statements, which is the default case, meaning that if your variable does not fall into any of these cases, which these are the cases, by the way, on the left, I'll go into that a little bit more. If it doesn't fall into any of the specific cases, it'll then default to whatever the default case is. So the format internally, though, as you see, is the case that you're looking for, which I've used as local parameters up here in the finite state machine. You have state 0 is 0, state 1 is 1, state 2 is 2, and state 3 is 3. If the current state falls into any of these conditions on the left, then the operation on the right is performed. So in this case, it is determining the next state logic for a finite state machine. So in this case, if the current state is state 0, the next state becomes state 2. If the current state is state 1, the next state becomes state 3. If the current state is state 2, then the next state becomes state 1, and so on. Now, keep in mind, there is kind of a priority to this operation. If more than one case is met, the first case that occurs is the one that is performed. So, for example, let's say, and this isn't really a feasible thing, but just for the sake of explanation, let's say current state is both S1 and S2 somehow. Well, as it goes through this case statement, it checks as 0, it's false. doesn't perform that operation. It checks state 1, that's true. It performs that operation and then stops. It does not reach state 2 or state 3. So it works like an if-else statement, or if-else statement would work in like a programming language, where it stops once it's found the first case that is true. And then with default is similar to the else aspect of like an if-else statement. Whereas if none of the cases in that case statement are true, then the default case is performed and that operation happens. Now, if you wanted, I put this as a note here, but if you were interested and you just, in a case like this where there are all of the possible choices are representable in a simple way, then you could just replace the last choice or the first choice or any one of them with default. Not that you have to, but you could. But case statements are a really powerful tool for shrinking your code and making your code much more readable when you have dozens of potential outcomes. And it just is much easier for that. The next thing that I want to talk about is instantiating modules in other modules, basically. So a top module, for example. In this case, instantiating modules can both save you time as well as make debugging significantly easier. So this kind of goes into the concept that I was talking about earlier of having only one module per file, and then whatever you're trying to build, so later when you go on to work on the single cycle processor and the various different processor designs, make all of the components in separate modules and then just instantiate them in something called the top module, which a top module is basically just a module that functions as a place to kind of put the jigsaw puzzle together. Think about it like a jigsaw puzzle. All of your modules are the individual pieces, and your top module is the table that you put it all together on. And in this case, one of the things that I wanted to talk about when it comes to module instantiation, because overall it's a fairly simple concept. You have your module name. In this case, it is a register, so I'm going to close all of these extra modules for a second, and then I will show you the register module that I have here. See, the register module has 4 inputs and 1 output, and 1 parameter, this parameter being the data width that I discussed earlier. So when you want to instantiate that module, you have the module name, and the first thing that you have is the parameters. Now, keep in mind, you do not actually have to declare the parameters, because when you make the parameters in the module itself, you have to give it a default value. You cannot leave it blank. You need to give it a default value. In this case, the default value is 32. So let's say, and this is actually fairly prevalent in your processor assignments, especially once you get to the pipeline when you have to have registers in between. Everything will be 32 bits because it's or most things will be 32 bits. Any data will be 32 bits because it's MIPS. So your default value will work just fine in several occasions. Not all occasions, because some things aren't 32, like program counter, or actually the program counter is 32, but well, it doesn't have to be 32. You can make it whatever size you need, but not everything is 32 bits. Like register addresses and stuff like that are 5 bits. But in the case that many cases, the 32-bit will work. So you actually could very easily just not have this section here. Like, this could very easily not be there. But what you do absolutely have to do for any module you instantiate is you have to give it a name. You have to give it a module name, which I have here as reg1. Keep in mind, you don't want the name to be any kind of a keyword. So if I were to delete this and do reg, that's not good, because that's a Verilog keyword. The all caps version does work, but I typically just say add numbers to things, because even if you add numbers or add a very unique name, because you'll often be instantiating several of that module in a top module, and this allows you to uniquely identify them. Plus, on top of that, it is required by the Verilog syntax. Now, one other thing I like to note here is there are various ways with the parameters themselves that you can use them. Now, in this case, you could very easily just have the number 32 in the parentheses, because you don't have to give the parameter names per se. You can just do a comma separated list of the values, but you have to make sure that they're in the right order as they are in the module itself. So if you had several parameters, let's say, let's see, which has several parameters. My clock divider has several parameters, or 2 parameters. If you were to instantiate this module and just put values in, you have to make sure that they're in the right order. So your input frequency has to go first, and then your output frequency has to go second. So you could just do, let's pretend that this is that clock divider. You could do the 1 million or whatever, and then you do your next number, and then you're fine. But you can also just do this. But I prefer, for readability as well as just so you know what corresponds to what when you're debugging, because for all you know, you could potentially enter the wrong number for your parameter and cause issues in your module. So you know what value corresponds to what. I prefer to do the named parameter method, which is with the dot and then the name of the parameter inside that module, and then parentheses with the value for that parameter. Similar to how you do ports. Now, once you have your parameters, once you have your name, it's onto the ports, which works a similar way to the parameter way that I discussed before, where you're better off just doing the dot name and then parentheses and then a comma separated list of those to do your various input-output ports. Now, one other thing, or a few other things that I want to mention here before we move on from instantiating modules, is there's a few things that aren't really discussed in the book, that aren't really covered anywhere, that I want to let you guys know you can do, because it'll save you a lot of time when you're writing your Verilog. Is you are able to do 3 things, actually 4 things, that I recommend you all take advantage of. The first thing is I recommend you add extra control signals, so extra control signals to your modules, especially things like the registers. I say just add the enable signal to your register, even if you're not going to need it. Even if you don't need to use an enable every time you use a register, you can do something that the book doesn't tell you, which you can already see here, is that you can actually use constant values as well as like logical operations and various operators within your port declaration. So what this allows you to do is, let's say you have a register, in this case, this register. You don't need the enable signal, but you don't want to have to write Verilog for 2 different registers. You don't want to have a register without enable and register with enable. So you just have one register with the enable, and then you put a constant value signal to that enable, or whatever control signal it is, to then allow you to have basically a constantly enabled module. So you don't need to worry about the enable switch. Just give it whatever constant value will not interfere with the normal operation of your module. As well as with the logical operations, rather than having to do a separate assign statement or a whole separate module for, or adding a gate for the logic operation, let's say, you know, your reset, there's, and in this case, in the later assignments, there are several things that drive a reset sometimes. You can simply just have the module reset at when something or something else happens. So like, let's say there's a signal that is already declared somewhere that's called clear, and then you have your normal like system reset. Well, you can have it such that it resets either when reset or the clear signal are high. Now, of course, it's going to give me an error right now because I don't have a clear signal declared anywhere, but that is a valuable tool that you can use to just, one, reduce the overall lines of code that you use, because you don't need to always have like an additional line of code just for something as simple as an OR of two control signals that are driving a different control signal in a module. So just keep in mind that you're able to do that, as well as one other thing that the book never tells you that you can do. But let's say you have a module, in this case there's none that are here, but let's say you have a module that has an output that you don't always need. So let's say you make a ALU module, an arithmetic logic unit, that has outputs from both overflow and zero and divide by zero and all these other special cases, and it has outputs or output flags to let other modules know if any kind of error occurs. But let's say the module that you are currently writing doesn't need all those extra signals. You can simply omit the ports. You don't have to have the ports there. So you can simply not define the port when you instantiate the module and don't have to worry about it. As long as, of course, the port isn't, crucial to the module's operation. Like, you can't just omit the clock port. The register's not going to work. But if, like, a module like an arithmetic logic unit has an overflow and you don't care about the overflow for what you're doing, because let's say it's not possible with the way you're doing something, then you can just simply omit the output. You can omit the port. Now, moving forward from that, that's the end of kind of instantiating modules. Those are just things that I wanted to cover that the book doesn't really discuss that you are able to do. The next thing I want to talk about now, and this is probably the thing that most of you are unfamiliar with, is the memories. Now, there are various types of memories described in the book. I have two different ones that I've created here. One of them is an asynchronous single port RAM, or asynchronous read single port RAM. So this basically is a RAM that is always reading from whatever read address is provided, and is able to be written to at a positive edge of the clock. So in this case, you have the signals of the clock, the write enable, the read address, the write address, data in, and data out. Now, when you start working on the single cycle or even assignment 0, where you make the register file and the data memory and the instruction memory and all that, keep in mind that I want, and the course asks of you, to use the signal names provided in the textbook, just to make things simpler to understand. The textbook has things for example, the register file, which is just a dual port RAM. That has specific names for the ports. For example, its enable signal is not just write enable, it's register file write enable, RFWE. And for example, the two read addresses, it's RFRA, register file read address 1, register file read address 2. And then you have like the register file write address 1, or register file write address, just RFWA. And then you have like register file write data, RFWD. Just use those names because it makes it easier to, one, for you to read the book and see what corresponds to, like what port on some module corresponds to a port on another module, as well as for me to grade or help you debug your modules. or whatever TA is doing this in the future if this video is being watched by somebody after I'm no longer the TA. So just keep in mind that when you write the modules for your assignments, please use these signals in the book just because it makes it much easier for everybody involved. But in this case, to explain what the signals do, you have your clock, of course, which is just your clock. Your write enable, which allows you to turn off or turn on the ability to write to the RAM. So if you don't want something writing to a RAM location and potentially interfering with what is currently stored in there in a negative way, you can obviously disable the writing capabilities. Then you have your two different addresses, which are for reading, which uses to determine what goes to the output port, and then your write address, which determines which position in your memory your input data gets written to. And then, of course, you have your data input and you have your data output. Now, this is where the power operator comes into play. So, as well as the concept of arrays. So, when you have your RAM, now you have your module inputs, outputs. I have two parameters here you can see. I have DW, which stands for data width, which is 8 bits. So it means every piece of data is an 8-bit vector, or 1 byte. And then I have another parameter, AWL. Now, that might not be apparent immediately from the name, but that is the address word length, meaning that is a 4-bit address, meaning that it can represent 16 potential locations, 0 to 15. Now, when you declare your memory, which is the array of vectors, you can see here, I just have the name RAM, just a simple name. And of course, the vectors themselves are 8-bit, meaning that it's the data width 8 minus 1, which is 7, and then 0 to 7, giving you 8 bits. And then you have the number of vectors. Now, this is where the power comes in. It is 2 to the power of the address word length, meaning that it can represent 16 possible locations. So 2 to the 4 gives you 16. And then you subtract 1, of course, because you include 0 to the left, as you can see. And that gives you 0 to 15. Now, I always recommend that you simply do this 2 to the power of the number of address bits minus 1, because in reality, you're not going to, for example, if you have a memory with, let's say, a 5-bit address, which would be 32 locations, that memory isn't going to, for some reason, only have 15 locations. It's going to have all 32 because there's no reason to have more or less memory locations than what you can already, because you're already designing all those address bits anyway. So most memory locations are going to have the number of locations correspond to the number of bits. So just simply do this method here of the 0 to the, and then 2 to the power of the number of bits minus 1. Now, but when you do this, keep in mind that you don't want to use an address width of too large, because your FPGA, which is what the tool is always trying to cater to, has a limited number of resources, and you can't put, like, for example, 32-bit address width, even though that's technically what like a MIPS processor uses. You can't put that because that's more than is going to be on any FPGA that you buy for a reasonable price. So just keep in mind your address word size, because that would give you, absolutely would give you an error in Vivado when you tried to simulate. If you did 2 to the 32, you'd have a massive issue. One other thing here that you can see kind of commented out is this block of code here. Now, the reason why I have it here is because the RAM like this, normally you don't have it initialized to anything when you synthesize it, because it's a RAM, so you have to write to it for it to have data. Now, when you're simulating only. So when it's something that you're not actually going to be synthesizing to an FPGA and you're only going to be using for simulation, which is this class, you can use this little block of code here, which will allow you to initialize the entire RAM to 0, so that when you're debugging, you don't see a wall of X's, a wall of red X's. You just see a bunch of zeros and then the data that you need. It makes it much easier to find errors than if you didn't do this. So this is basically just a for loop using an integer that will loop through every location in the memory and set it to 0. And if you look here, the actual code for the memory itself is very small. It's basically just at the posage of the clock. If the write enable is active, the data in goes to whatever address the write address is pointing to, and just in general, it's always outputting whatever the read address is pointing to. So the actual code for it is very simple. It's just the process of setting up the memory that a lot of people are confused with. And the next thing is the ROM, which is where you start getting into initialization files and .mem files. So this is what you'll have to, this is a more simple version. This has no write port at all. This is a true read-only memory, which is kind of what you'll end up using for your instruction memory. But the what you have to do is you have to use an initial statement, which I'm going to show you actually live, because this is something that is very important to your ROM working. So what you would do for your ROM is you have, similar to the RAM itself, you have your reg and then your mem definition, right? In this case, it's named mem instead of RAM. And to fill the ROM with the value of your mem file, or all the values in your mem file, you will do initial begin, and I just like to do the end immediately. And then in between, you use the function. There are two functions. There's $read, $read mem, and then you can either do read mem b for binary or read mem h for hex. So you can either do read mem h or read mem b. Now, something from my experience that I've noticed in other classes is that if you ever want to start getting into synthesizing your modules to an FPGA, read mem h has caused me issues in the past where read mem h does not synthesize ROMs properly, but read mem b does. I've never had a problem with synthesizing a ROM or a lookup table or anything of that sort using read mem b. And the syntax for read mem b is very simple in that you have your read mem b, and then you have the file name. In this case, I have a parameter here, but you could also just take that text and put it here. I'm going to put the parameters, though, for simplicity's sake. And then the name of the memory that you're trying to fill, which is that reg that you made there, that array. Obviously, and then with a semicolon at the end. Now, what this will do, and the way that readmem-b, or readmem just in general, behaves, is you have a mem file, which I'll show you how to create in a second using Verilog, or using Vivado, the tools provided, rather than having to try to create a file and change its extension and all that. That's a pain. All you have to do, or the way that this works, is you have the size of that memory. In this case, I have 3 bits on this, so it's only 8 locations. And that readmem will try to find 8 locations, or 8 values of the size provided. In this case, it's 8 bits, so it's going to try to find 3 sets of 8 bits to fill the memory in with. starting with the beginning of the file. So now I plan on showing you how to actually create the .mem file. So what you do is you hit the plus up here to add a source like you would normally. And then it doesn't truly matter whether you pick design or simulation. I typically go with simulation. Um, you can select next, and then you create a file. And in this dropdown, there are several options. They have Verilog, Verilog header, system Verilog, VHDL, and memory file. And then you can name it whatever you want. I'm just going to call it ROM init. As like a ROM initialization. And I'm going to click OK. I'm going to click Finish. Now, in your simulation sources, there will be a new, or whether you pick simulation or design, doesn't matter, there'll be a new folder called memory file. You can click on this, you open it up, and it's blank. Okay, now at this point, what I like to do is, well, first you put your values that you want. So in this case, there are 8 potential values of 8 bits. So you just can put whatever you want. I'm just going to fill it with ones for now. It doesn't matter. 1, 2, 3, 4. And you can take this and just copy it as many times as you want. And then to be safe, especially in some cases where you have several, or you have a much larger memory than needed, which you'll have in the case of your data and instruction memories, you can take this and then just add a bunch of 0 lines afterwards to make sure that even if, for example, you don't occupy every space, the rest of them get initialized with 0, so you don't ever accidentally get an X of some sort. It's fine if you have more locations in, or more pieces of data, like more extra zeros in the file than are in the memory, because the way that the read mem works is it starts from the lowest or the first position in the file and tries to fill the memories based on that. So it's going to start with from here and go down. So it's going to start position 1, or the first line fills position 1 in the memory, position 0 in the memory, position 2 or 1 in the memory, position 2 in the memory, 3, 4, so on. And so that's basically how you create memories and how you initialize memories that need to have data when they begin. So for like things like your data memory or your instruction memory for your single cycle processor, that's how you create the .mem file. And the ROM here, this is how you initialize it. So this is the one exception of where you'll use an initial in a module, is with ROMs like this where you're supposed to have a value already in the memory when you begin. This is the one exception that you'll have an initial. But that kind of sums up the memories there with how that works. You can see, though, how having this parameter is beneficial, because if you, and you'll see this once you start writing the, once you start working on the processors, is there are going to be several different example code sets that you should be running on the processor. And rather than coming in here and constantly changing a file name or constantly altering a file with a set name, you can have all of the files. You can have like 5 or 6 code files and just change a parameter to change which one it reads when you run the simulation. So I recommend in your memories you add a parameter for the file name. And because we created it through Vivado and it included it in the project, you don't need to do any kind of file location like tracking in the name. Like you don't need to do, like C:// whatever various locations. You can just do the name with the extension and it'll work. But that kind of sums up the memories, and with memories, that sums up what I wanted to cover with writing Verilog. So that covered some key operators that are not really discussed as much in the book. It went over using how you can use always blocks, using combinational versus sequential logic. Actually, there was one other thing I want to discuss before I move forward with the always blocks, is the various types of sensitivity or edge or sensitivity lists. So I don't know if you've heard the term sensitivity list before, but what that means is the always block will update anything or run the lines of code in the always block based on a sensitivity list. So whatever signals it's looking for is the sensitivity list. In this case, this always block up here, the sensitivity list for this always block is the clock signal and the reset signal. And by using the prefix pause edge, there's also another prefix neg edge, which is the negative edge, of course. And by using these two, and by the way, the comma is equivalent to an or. So in this case, the always block is triggered by the pause edge of the clock or the pause edge of the reset, meaning that this is an asynchronous reset. So that you can reset even when it's not at a clock edge. If you wanted a synchronous reset, you could just remove this pause edge, and then at the pause edge of the clock, if the reset is high, it'll reset. Now, the reason why, even though I have this asynchronous reset here, I have this if-else statement. The reason why that is because the reset triggers the entire always block. You want to make sure that you don't accidentally, because if there was no if-else statement here, if it was just current state equals S0 and the current state equals next state, you just have a situation where your reset is just immediately triggering the next state. So you need to be careful, and whenever you have an asynchronous reset like this, make sure you have an if statement that checks if it's the reset signal to make sure that the reset doesn't also trigger the rest of the always block. So just be careful when you use that. And then there are this always block here where you can use the, in this case, it's combinational logic. So this one, of course, was sequential logic because it was checking for the positive edge or the positive edge of something. In this case, it is a combinational block because it's checking for just a level change. So when you have it like this, right, so when it's always at the current state, it's checking for a level change. And what that means, especially with this because it's a vector, it means if anything changes in that current state value, it'll update the always block and run everything that's inside the always block. And then you might be curious what this is. The always at star is the simplest way to do combinational logic, because what always at star does is it makes it so the combinational block updates based on any signal that will change the output. In this case, it's a little different because this is a case statement, but if there was any kind of equation in here, it would update also based on the right-hand side of that equation, meaning any of the actual operands in the equation would update, or anything changing in them would update the output. Basically, meaning that this symbolizes true combinational logic, meaning any symbol or any signal that will change the output will trigger that always block to start and actually update what gets outputted. So at star is basically true combinational, and then the at above is combinational, but you only want it to be sensitive to the signals that you provide. So for example, if you had several signals that changed the output, but you only wanted the output to change if one or two signals change, then you could choose them specifically. And then this is at the edge of a clock. And also this demonstrates that or, like I was discussing. But other than that, that wraps up the section on writing the functional Verilog modules. The next section is going to be writing test benches with the focus on just the RAM itself. Okay, so one of the second to last thing that I want to cover is test benches now. So the test bench that I have here is for the RAM module that I showed off earlier, which I chose that module because it shows kind of all of the main aspects of running a test bench on Lovato. So when you have the module that you want to test completed, like this RAM, the next thing you need to do is when you go to make your test bench, is you create the file. The file will have a normal looking module file. Just delete the parentheses and just the module declaration should just look like this. Module, the name, it's kind of standard to put TB at the end, whether you do underscore or whatever, just put TB to signify that it's different than the module itself. Also, you don't have to put the exact module name if you don't want to, because here, for example, my module name is async sp ram. And this test bench is just ram underscore tb. Once you have the module completed and you want to make your test bench, you should start by declaring all of the variables that you're going to use and all the parameters that you want to use. So first, the RAM has 2 parameters to it, so I declare those 2 parameters. In this case, I'm using the same values, so I could have omitted them, but I put them here just to demonstrate. I declare the 2 parameters, DW and AWL, and then I declare a third parameter, just because it allows to do some of the other things later easier, just using a name rather than constantly doing this formula everywhere. So I chose this parameter because it's the number of memory locations, so this helped with several of the loops that I'll show you later. The next thing is you want to start going through the input-output ports on the RAM and declaring them. Now in this case, because we're going to be running the test bench inside of an initial block here, which I'll explain a little bit more on the functionality of that in a moment. An initial block is a procedural block, and if you remember what I said earlier on in this lecture video, anything that is going to be assigned to inside a procedural block needs to be of type reg. So all of the variables that are input ports to the module are declared as a type reg. Anything that is an output port of a module, which means that it's not going to be driven from a procedural block, it's being driven from the module, needs to be a wire. I also have an integer here you can see, and this is where I said integers come in handy when it comes to simulation rather than inside modules, is for looping. This integer I is going to be used as loop control for 2 different loops. So here you have the module instantiation. You've already seen this. I went over that with the register. I have my parameters, my data width, and my address width. And of course, I can simply just use the names because I created the parameters up here. So I can easily, if I wanted to change the size or the number of address locations, I could just change that up here. And then we have all the module ports, which I've already shown before with the register that I showed off earlier. And then in this case, I have the module name DUT. That's a common module name for test benches. You don't have to do this, but it's just a common name because it stands for design under test. Just a common naming scheme. You don't have to do that if you don't want to. The next thing that I want to discuss with the test bench is something that comes in handy for basically everything that you're going to do in this class, is clock generation. You're going to need a clock signal for just about everything you do in this class and almost everything you do with Verilog and any kind of sequential logic. So the easiest and my preferred way of generating a clock signal is this simple one line right here. where you have always and then a duration. This is a half period, so in this case it's a period of 10 time units, which is defined up here by default as 1 nanosecond, so this is a 10 nanosecond period. Not that it matters, the time units aren't the biggest deal. I say just leave it as the default time unit up top. But in this case, this delay, which you see here with the pound sign, in test benches you use pound sign followed by a number to signify a time delay. And in this case, you can simply do always with a time delay, meaning that this is going to always loop every 5 time units. And the code that is going to run, since it's one line, we do not need to use a begin-end block because it's just simply one line. You can simply do your clock signal, in this case mine's all caps, doesn't really matter, with a non-blocking assignment followed by the not symbol, which is the tilde on your keyboard, and then the same name of the clock signal. This basically is just saying every 5 time units toggle the signal to the opposite, meaning that, of course, you have a 2 times of this delay period. So that is just the simplest way for clock generation, and all of your actual test code should fall in this initial block. You don't there are other ways to do test benches, but for the sake of this class, this is the easiest and most readable way to do test benches. And what you do in the initial block, and the way that initial blocks work, is for simulation, the initial block starts at time equals 0. So anything in this initial block begins at time equals 0. So until you put any delay, you assume that every command happens at time equals 0. So what happens here is this clock, so you set your clock to 1, meaning that your clock starts at high. So, and this will trigger any always blocks in your modules. This is an edge per se, so it means that this initial set will consider as an edge. I have my write enabled low, my data in as 0, my read and write addresses as 0. This is just the initial case of your inputs. Then, to make your test benches smaller, you do not need to put a bunch of delays and a bunch of different commands. You can use loops like you would in any other programming language. In this case, I'm using a for loop. Though keep in mind, one thing that you cannot do is you cannot declare the integer I in here, like you would in something like C or C++, where you can just do for int I equals 0. You have to declare the integer up here, and then you can put the I equals 0 in here. Other than that, it's formatted basically the same as as you would in C, though Verilog, I don't use the ++ operator, as I don't believe Verilog has a ++ operator, so you just have to simply do I equals I plus 1. It's not really a big deal, but that's just what you got to do. And once again, with anything that is multiple lines, you have to do a begin-end block. And in this case, what I did here is to demonstrate that you can do it with delays. You don't have to do it with what I do down here. You can do delay 10, which means it waits 1 clock cycle, or one clock period. And then the way that this works is when it says delay 10, anything that happens at this time, if you do the anything that happens at this time will be considered to have happened before this clock. So if you do delay 10 and you change things, whatever you changed will happen at that clock cycle. So the first clock cycle happens here, you delay 1 period, and the second clock cycle when it starts will be using these signals, meaning that at the second clock cycle, the write enable goes high, the write address goes to I, in this case starting at 0, and the data in is assigned to I plus 1. So it's going to write 1 to the first location. It then repeats as long as it's less than memlokes, or memory locations, which was that local parameter I showed off above, or that parameter I showed off above here. That was just calculating the total number of memory locations, which is that 2 to the power of AWL, meaning that in this case there's 16 memory locations. So it goes from 0 to 15, filling each memory location with a value. This is just a test bench for this specific module. Of course, the code in here will vary significantly depending on what you're testing, but the goal is to show you the overall format of how a test bench works. And this is basically the format for every test bench you should be giving or demonstrating to me in this class, and basically just in any time you write Verilog, is you have all of your declarations of your variables or parameters or integers or any kind of variables that you're going to use. You have the module that you're testing, and then you have, if you're using a clock, your clock generation, and then you have your initial begin end, which is your actual test code. In this case, declare the initial signal conditions. You loop through filling the memory. Now, this delay 1. So keep in mind, like I said, this 10 is happening at that clock edge. So I don't want to change or lower the write enable yet, because the write enable, if I lowered it right after this for loop, it would still lower it before calculating or before loading that last location. So that last location would not get filled if I put this here. If I put this here, that last location would not get filled because this would take into effect before the clock, because this is still happening at this time. So what I personally do to handle this is I just usually drop just a simple 1 delay, just to make sure that it doesn't happen at the same time. You don't have to worry about that all that too much. Just remind yourself, though, that if you're going to do that, if you wanted to continue using this delay method, then what I would recommend you do to get to the next clock cycle is to delay 9 rather than delay 10, because of course if you delayed 10, it'd be after the clock edge. But since I'm using the next technique that I'm going to show you, that's not required in that case. But in most cases, what I would have you do is just simply do this to ensure that it happens at the properly at the clock cycle, right, at the clock edge. But what I do here to demonstrate is another command that I actually like a lot, and I think is one of the most useful commands that is present in Verilog, is the repeat command. So before getting to that, of course, I delay 1, I lower the write enable because we've already filled the memory, there's no point to write anymore. I reset my loop variable to 0. And then I use this command here, which is the repeat command. Basically, this is, as the name suggests, whatever block of code follows the repeat command will repeat by the number of times presented in this parentheses. So there are 16 memory locations as calculated up here. Therefore, this repeat command will repeat 16 times at the pause edge of the clock. So for 16 clock edges, this command will repeat. And what I have in here is this just increments I, and in this case I'm using non-blocking assignments, as you can see, because I want to increment I and read the address at the same time without altering I. So what I do here is I just do non-blocking, and the read address is equal to I, and then I gets changed at the same time, and the read address reads the previous version of I and not this changed version. That repeats 16 times at the edge of the clock. You don't need any delays because it just waits for the clock edge. And then the most important thing, though, that I want to add here that I've seen a lot of people miss when they do their test benches is this little line right here. $finish should be at the end of every single one of your test benches. Because if it's not, the test bench will continue to run until it hits the time limit, which is something I'm going to discuss in a second as well, because many people I discovered last semester were unaware of this setting that I'm going to show you in a moment. But what this does right here, before I move on to that, is this basically just terminates the test bench. It's like putting a return 0 at the end of your C code, or just a return in general at the end of your C code. This should be there at the end of every one of your test benches. So there is also a while loop. I'm not going to demonstrate that here because it's basically the exact same as it would be in a C program. Just remember, blocks are not with curly brackets, they're with begin end sections. But the while loop functions the exact same as it does in any other programming languages, so I'm not going to cover that. But now I want to show you all the simulation time limit, because in this class you will absolutely exceed that, and that would, and commonly will make people think that there's something wrong in their design, when in fact their design is just fine. It was just a Verilog setting that was wrong. So if you click up here, you'll open this settings tab, and in this settings tab, click on simulation. Now there's a lot of tabs in here. It's very, there's a lot of them, but click on simulation and you see this right here, xsim.simulate.runtime. What this does is this sets a hard cap on how long your simulation runtime can last. Now what I typically do, and this also corresponds with the $finish down here, is I just extend this to a value you'll never reach of 1 second. You're never going to reach that in this class ever. No, none of your designs should ever reach 1 second. Now, keep in mind, this setting is not a permanent setting. So it's permanent for this project, but when you create a new project, you need to update this setting every time, unfortunately. So just remember, make it a force of habit to whenever you create a project, you just, first thing you do, open up project settings. So open up project settings is the first thing you'll see, simulation, 1 second, enter OK. And there you go. Because if I go back, I'll show you, I'll run the simulation first, and I'll show you what happens. So right here, this is just a normal simulation. I'm going to run it. You'll pop up this window, of course. This is the waveform diagram. This button right here, if I ever tell you in class, can you hit zoom fit? This button right here will zoom to fit the entire waveform in that window. Now I'm going to hide these two and zoom fit again. Now you can see this only goes up to 330 nanoseconds. So if I were to close the simulation, go back into the settings and revert that to demonstrate what happens, and click OK. If I were to just for some reason add, let's say, a really long delay at the end here, and I save it. So this is 100,000 nanosecond delay at the end here. If I were to run this simulation with that setting left at its default state, you'll see that stops. Well, this is in picoseconds, but 1,000 picoseconds is 1,000 nanoseconds. It stops at 1,000 nanoseconds and doesn't go the entire way. You can see that it only does these couple changes. It doesn't do much. So it does, this is all of the, well, actually it goes much further than the whole way, but this is all your design goes, and then with that delay in the file, it should have gone to, you know, uh, a million or 100,000 nanoseconds. It stopped at 1,000. Now, if I close this, now normally, if you're only making small changes to your file, like if let's say you just go in here and you alter your Verilog design because something was broken, you don't need to close the simulation every time normally. Like, okay, oh, something didn't work, I had to change a thing, and then you want to rerun it and see if that change fixed it, you can click this button up here, relaunch simulation. You click that, and it'll just rerun the simulation. But with a change of settings, you can't simply do that. So if I were to go here and change this back to the 1 second that I was talking about, and you click OK, and then I try to relaunch it, it's not going to change. It's still stopped at 1,000 nanoseconds. So I have to close it, let it fully close, run the behavioral simulation one more time. And then now you can see that it went to much further. This will absolutely come up in your assignments. So remember, just at the start of your project, when you create it for the first time, just go and change that setting. Now, I'm going to fix this and show you a couple things that nobody ever showed me and I just figured out. And I'm going to show you them so that you can benefit. So there's a few things that you can do with this simulation window here. So you see here, there's a few things, first of all, that we don't need in here. So a few of them, like these, are parameters. Now, rather than having to click on every single one of them and hit delete, you can do something to save yourself time. If you just click on one, you can hit shift and then the up arrow, if you like, or the down arrow to stop or go back, to select multiple and then delete. Just hit the delete key. And so with that, it allows you to simply remove unwanted signals in bulk from the waveform. And the next thing, and this is going to be pivotal for you demonstrating your assignments in this class. Your best friend when testing modules is the scope and objects windows. So as you can see here, you have the scope and object windows. What these allow you to do is, as of now, the only signals that are displayed on the waveform, minus of course the ones I just deleted, are the signals that you created here. So let's say though you have an error that's shown up in your code, and it's not an error in any of the signals shown here. It's an error internal to your module. Well, without these windows, there's no way to see that, the internals of your module. But with these windows, it allows you to see the internal signals for every single one of the modules in the module you're simulating. Now, what you do is you go to the scope window, and when you're trying to debug, you try to figure out what module is causing the problem. Don't worry about this. This is just something that Verilog creates, or Vivado creates. You don't need to worry about this one right here. This is your this is your test bench with all the signals that you created in there. And then you have your module that you instantiated. Now, keep in mind, these are drop-down windows, so they might not be dropped down at the moment when you show up, but just keep in mind that modules that have instantiated other modules will have drop-down windows. And if those modules have other modules instantiated, they will also have drop-down windows. You can click on the module, and as you see here, all of the internal signals are up for display. Now, Of course, you can't really do anything with these because they show the signals at the end of the simulation. So they show the signal state at the end of the simulation. So if you want to see them as they're going, and I'll ask you to do this for the processor assignments because this is the only way to really demonstrate the memory locations themselves, is you can take the array that has your memory or any other signals that you would like and just drag them on. And they won't show up, of course, not yet, because they haven't. The only signals that have been tracked the whole way through simulation were the signals that it was told to track throughout simulation. So to get them to show up, you just relaunch the simulation one more time. And now that signal has shown up. And because it's an array or a memory, you can drop it down and you see all of the individual memory locations. So for the later assignments, the processor assignments, you'll be asked to demonstrate specific memory locations. And by specific, I mean the ones that are only the ones that are modified. So you actually don't have to drag this full memory onto the board if you don't want to. What you can also do is if you want to check specific memory locations, you can take that memory, drop it down, and select, let's say I only wanted to see 3 and 6, you can drop them in individually. Excuse that, there's somebody with a loud motorcycle in the background. But you can simply drag and drop signals into the waveform like that. So I'm going to drag the RAM back in, and another thing that I'll ask you to do, just for ease of reading, is you can also, well, there's a few things. You can make some cosmetic changes to this waveform for ease of readability. So for example, you can change the name in here. It has no effect on the name in the module, just simply on the waveform. So let's say in many cases in the memory and the register file, the registers in the register file have specific names. So let's say you wanted to have, let's just say for now, you have, oh, this is register T0. You can put T0. Register T1. You can put T1. And when you do this, it makes it easier to read and tell which register is which, just by looking at your code at a glance. Another thing that you can do to make it easier to check is you can add dividers. So this button here, when you right click, it says new divider. You can click and drag this divider anywhere you like, anywhere you want. So let's say I wanted to divide the addresses from the data. So let's say I have data in, and let's say I want a few different dividers here. You have control signals, and these are all the control signals, addresses. Let's see, a new divider, data. Just delete I because nobody needs that, and then the RAM. And if you want to differentiate these, you can color code them, divider color. Unfortunately, they don't have like a select wheel, they just have their presets, so you're just stuck with those. But if I wanted to color code them, you can. Like so. And as well, you can color code the signals as well if you like, though that becomes a little bit more challenging if you want to try to color a signal red, like this, for example. If you try to color it red, there's no way to tell the red X's really from the red signal. So I ask you not to use red, but if you use any other color, the red will still cover through from like the X's. I also ask you not to use blue, as in the dark blue, right here, or this blue right here, do not use that, because the color for undriven or Z signals, or high impedance signals, is that same color blue. So just avoid that blue and that color red. But everything other than that is fair game. But let's just do this. You can color code anything you would like. Another thing that I will ask you all to do is, by default, the waveform viewer will try to display the numbers in hexadecimal. Any of the data that you have, I ask that you use either, depending on the situation, signed or unsigned. In most cases, it's going to be signed decimal, because it's easier to check and see correctness that way. But that's just for like data and address signals like that. All the control signals you can leave as binary or just level and all that, as well as with the RAM. Annoyingly though, with the RAM, if you select the whole RAM and change it to signed decimal, it doesn't do it for all of them. You have to actually go through all of the individual ones, but luckily, because of the shift tool I mentioned, you can do that fairly quickly and change them all. So that's kind of just the things I wanted to show you all about how to customize your waveforms and how to use the Vivado environment to your advantage. Another thing, when you get errors, sometimes it is prudent to look at this TCL console down here, because when you get an error, right, and sometimes it's not blatantly obvious where the error is. Sometimes you can scroll through here when you simulate it with an error, and there will be little, see here, they are labeled as info here. You can also, there'll be some that will be labeled as errors, and you can use those to help determine where you might have gone wrong in your modules. There are also messages. Like, see, there is an error here, but not all of the errors matter. I also recommend you regularly discard this, because what happens is sometimes Vivado does not properly remove old errors, and you'll note if there's actual errors in this current iteration of the loop, they will not be deleted. You saw all of them get deleted right now, but that's just because they were all old errors. They will not get deleted if they are significant errors. And now you see, when I rerun this, it's just info blurbs. And the info blurbs are not helpful to you. Right now I'm going to purposefully cause an error in this module. Just delete that, save it with an error, try to run it, and then you see here, you have errors that show up here. It says compile step failed, detected error while running, launched while running. If I click delete here, it gets rid of all of the unnecessary things, and it just leaves you with really where the errors are. And that'll help you, as well as if you go here, you see all these red errors, error. Well, sometimes if you see up here, error, syntax error near end, and then you look over here and you look through this long list of the file location, and then it tells you at the very end, 28. That means line 28, there's an error. If you go to line 28, oh, there it is. Error at end. Let's see, what's the error? Oh, I forgot the semicolon here. There's the error. This can be very useful when debugging your modules. But remember to just delete the unnecessary, because you can also kind of check which ones show up, but you can just delete the unnecessary messages. And other than that, There's one other little thing I wanted to talk about, but that'll be wrapping up this lecture video. The one last thing I wanted to talk about is bit width growth. Um, Now, it's not that much of an issue in the processor assignments because you'll be using just always 32-bit data, so you don't have to worry about bit width growth. But if you're ever writing Verilog, you need to keep this in mind that whenever you perform arithmetic operations like addition or multiplication, or even potentially subtraction, um, that the bit width will and can grow. And with addition, the way that it works, I'm going to simply close the simulation now so I have a larger screen. Oh, actually, one other thing that I wanted to demonstrate. You can save the waveform, if you'd like, for that test bench. And if you close it by accident, and you did all these nice changes to make the waveform look nice, you can simply reopen it, and as long as you're test benching the same module, it'll pull up the test bench exactly how it was previously. So you can keep that in mind. But I'm going to close this again. And the one last thing I want to do, I'm just going to pull up one of the demo modules that don't really matter too much. And one of the things I wanted to show or explain, I'm just going to use comments like I did earlier, is when you're using addition, if you're adding two numbers, right? Let's say you're adding a 4-bit number. I'm not going to actually give the numbers, just the 4-bit number, and a 3-bit number. When you're doing addition, to properly be able to represent your output at all times, regardless of whatever the inputs are, your output needs to be the max of the two inputs, so 4 and 3 plus 1. So in this case, you need to have 5-bit output because the max of the two inputs plus 1. And multiplication is even more straightforward. If you had a 4-bit times a 3-bit, it is simply the sum of the 2-bit numbers. Therefore, it is a 4 plus 3-bit number, which would be a 7-bit number. Or 4 times 3, and then 4 plus 3 at the end gives you a 7-bit number. And that is what you need to represent the output. Now, keep in mind, the book simply tells you it's times 2. That's not the case always, because when you're using simple multiplication operators and you're not doing any pre-sign extension, and you're letting Vivado handle the sign extension for you, or Verilog handle the sign extension for you, then you can simply just use the number of bits based on this equation. So just multiply, or just add the two bit sizes together to get your bit output size. But other than that, that wraps up everything that I had to show you here today regarding Verilog, some Vivado tips, how to write your Verilog, how to write test benches, the general format of writing your Verilog, and all that. And like I said at the beginning, this is not an all-inclusive lecture. There are various things in the book that I didn't cover. The professor has the book covered, though, and has it posted on the Canvas page under the modules for Comp 470. So I recommend you strongly to read that book on your own time and learn Verilog inside and out for these modules, as well as I recommend you, when you're writing any Verilog module, to always, and regardless of how simple it is, especially when you're learning, always create a test bench for every module. Just test bench every module. Because if all of your modules work, and then there's an issue when you put them together, you know the issue is not in the modules, it's an issue with how you put them together. So you eliminate the issues within the modules first. So you write your module, let's say, because I know in the single cycle, which I believe you should be starting somewhat sooner rather than later. You have to have a register, you have to have an instruction memory, a data memory, a register file, some multiplexers, an arithmetic logic unit, a control unit, um, some adders, some various modules. There's a decent amount of work that goes into creating the single cycle processor. If you make all the modules first, test them thoroughly first, make sure they work first, then when you put them together, if you get any issues, then it's in how you put them together, because putting them together is a matter of just instantiating modules and connecting things together. Also, uh, don't make a bunch of the same module, utilize parameters. In the past, I've seen people make basically 8 of the same register with different names, not knowing that they can make one general register and reuse it. So please save yourself the time, the work, the extra effort that you don't need to do, and reuse all the work that you already did. But with that, that concludes this video lecture, and hopefully it was beneficial. Sorry if there was any kind of background noise or anything of that sort.